Let's start. How are you doing?
Pretty good.
Good. How are you?
Good, thank you. Can you hear me well?
Yes.
All right, great. Okay, so what we're gonna do today is to start from the basics, from the world description and so forth. Now, again, you know everything I'm going to talk about in one level or another, because you've been taught about all this stuff before. Now, my goal is here for you to actually think back and try to recognize those things which a lot of people get missed. Like, it's like sort of in the first class, they tell you about, like, system of coordinates and so forth. And then you tend to forget about it. And at least I did. But then at the later time, it actually bites you back, and you have to return back and remember what they told you about. And then you notice that some things which you glanced over is actually the most important ones. And that's what I'm going to try to do today. Although, as I said, it's many things are sort of trivial and will be, and you know all of them, most of them, right? Most of them, right? Because at the end, I'm going to talk about something which is, I think, very, very cute and one of the best mathematics I know. And I think it's a lot of fun, and it's a summer class, right? We're supposed to have fun. So that's what I'm going to do today. So let's think about the physics, right? What we're trying to do in physics. What we're trying to do in physics is to describe the physical world. Now, it's actually two different processes. The first one is that there is a physical world which is completely independent from observers, from us. Right? There are some forces acting, some things moving, planets go around, and they would go around whether we observe them or not. But we'll return to that point. It's actually also a non-trivial point, but we'll return to that later. And but nevertheless, we intuitively can assume we understand that there is some physical world, and it exists, and it works on its own, right? There's some rules there's some laws, what we call laws, right? The physical world doesn't know any laws. When you throw a stone, that stone doesn't know Newton's laws. It just goes, right? So what we actually want, we want to describe that world. That is the first step. The next step, we want to understand it, why it works the way it works, right? And make some predictions based on our understanding, and then eventually make some devices based on our on those predictions, understanding, and so forth. But the first step is to describe it, right? And how do we describe emotion? How do we describe something, some physical process? Well, you need to invent some language to do that, right? And that language is actually very natural. It starts with introduction of for simple mechanical system, and it starts with introduction of system of coordinates, right? You know that, right? And but what I want you to understand is that this is completely natural process to introduce a system of coordinates. That's what you do without actually knowing that you're doing it. It's just a name for something which you do anyway. Think about it this way. Imagine that you went to a basketball court, right, and take a ball and throw it from the other side of the court and made a hoop in one shot, right? Can you imagine that? Now, of course, no one has seen it. It never happens when someone's observing, right? So now you want to brag about it, naturally, right? So you want to describe to someone what you've done. That makes sense?
Yeah.
How would you describe it? Well, you will say that I took a ball and threw it from the other side of the court, right? Like, I have 5 yards to the right from the center. Something like that, right? Is it completely natural? But do you recognize that you actually established a system of coordinates? That's exactly what you do. You pinpoint your position by telling the other person where you need to go. You need to start from the hoop, go to the other side of the court, right? And move like 5 yards to the right. That's exactly the system of coordinates. You're introducing it without actually knowing that, without just using that word, right? System of coordinates. Well, we just call that introduce a system of coordinates. This is what you need to describe the process. Now, I want also to point out to emphasize that this is the system of coordinates needed for your description. Right? It's not needed for the ball to go to the hoop. Right? The ball doesn't know about that system of coordinates. If you use some other system of coordinates, the process will not change. The description of the process will change, but the process itself will not. It exists without your system of coordinates. And it works the way it works without your system of coordinates. But in order to describe it, you have to introduce the system of coordinates. Right? That makes sense? It's a very simple idea, right? Now, I also want to emphasize another thing. Just think about it, that you again trying to describe the same process as you shooting the hoop from the other side of the court to someone who actually never seen a basketball court. Then, for that person, your description will make no sense whatsoever. Right? That makes sense? Because what is the other side of basketball court? Or what is a yard? Or what is that? Right? So, in order to do that, you first have to agree on some common system of coordinates. You have to establish some system of coordinates with both you and the person you're talking to understand, right? And that's exactly why all the professors require you to draw a system of coordinates. Because when we look at your solution, must know which system of coordinates you've been using. Otherwise, we cannot do anything. We cannot understand. There is no way to understand. There is no universal system of coordinates. You have to establish it every time, and we have to agree on it. Well, it doesn't. But you remember, the process does not depend on how you observe it or how you describe it. So it doesn't really matter which system of coordinates you use, but you have to use something, and we have to agree on it. Or you have to tell me which system of coordinates you use in order for me to understand what you're actually doing. It's also quite important for your own good, because without introducing a system of coordinates, you actually don't really know what you're doing. How you describe because all the laws assume that there is, all our formulation assumes some sort of system of coordinates. And that's exactly what's the biggest problem in the majority of people's students' solutions for the second problem in the last homework. Remember the collision of two particles. All right, that was a very majority of you presented exactly the same solution, and I probably know why. And but that was a very marvelous solution because pretty much every step there was wrong. All right, I don't know where you got it. I don't know how you come up with that solution, but it was obvious that you didn't think what you write there. And the first step, which was wrong, is that the system of coordinates was not introduced. So what you write there makes no sense simply because you use the same notation for different things. That R, which was introduced in some place, was a completely different R, which was introduced in the other place. But you cannot capture that kind of mistakes because you didn't introduce the system of coordinates. You didn't introduce notations correctly. And that's the first step which always must be done. Otherwise, there is no way to avoid mistakes. Okay? That makes sense?
Yes.
So I want you to use that experience, right? In order for future. You know what experience is, right? Experience is the sum of all the mistakes you've made. So it's very important to actually make mistakes on your own and then analyze them. That's how you learn. That's the only way to learn. That's what's called experience. If you never make mistakes, you don't have any experience. If you don't solve problems on your own, you don't make your own mistakes, then the only thing which you learn is how to solve problems which have already been solved. You do not learn how to solve a problem which you've never solved before. But that's what we want, right? We want to solve problems which haven't been solved before. Otherwise, there is no progress. All right, so we need to introduce system of coordinates. Again, there is no difference which system of coordinates you introduce, but you have to introduce some system of coordinates. You have to have a common language to use to describe the process which we want to describe. Okay? So there are different systems of coordinates. There's Cartesian coordinates, and they are, in many cases, they are most useful, but not all of them, not all the time. There are some other system of coordinates, and polar system of coordinates. You know those. And but there are plenty of others. You can invent your own if you want. And in some cases, a problem just calls for some specific system of coordinates, which you have to invent. Then you do it, but you have to tell everyone what you're using. All right. So when you introduce a system of coordinates, then you see that I introduce system of coordinates, and you can introduce a system of coordinates. And those system of coordinates do not have to be the same. But if we describe in the same process, the answer should be the same at the end of the day, right? After all the calculations are done. So if you're talking about that ball going to a hoop, if I calculate something in my system of coordinates, you calculate the same process in your system of coordinates, the answer must be the same. The ball get into the hoop, or it didn't, whatever, right? Because the process should be independent of how we describe it. So there is also there's a question how you change from one system of coordinates to another, and that leads to some very important difference between different quantities. There are quantities which are completely independent on the system of coordinates. Their description completely independent of the system of coordinates, and those are called scalars. For example, energy, mass, charge. Those are just defined by some numbers, right? And that number will be the same in every system of coordinates. It doesn't matter. It doesn't know anything about system of coordinates. But there are some other things which also involved there, and they're called vectors. Right? Vector again by itself is independent on your system of coordinates. It's just vector, right? It's just something. Here is a vector, right? Here is a vector. But I can describe it in different system of coordinates, right? I can introduce this system of coordinates, and then I will describe it by components of this vector on this system of coordinates. This is x, this is y, right? Right? But I can easily also introduce a different system of coordinates. Let's say this one. It's also a system of coordinates. There is nothing wrong with that. I can use that to describe all the space which I have. Then what I have is that the components of the same vector on this system of coordinates, it will be this one, right? This one and this one. That will be the component. The components, these numbers, will be different in my system of coordinates. So white system of coordinates is your system of coordinates, red system of coordinates is my system of coordinates. Right? They will be different. The description of the vector will be different, but the vector will be the same. Does that make sense?
Yes.
Yes.
So it's one of the reasons why it's very important to introduce a system of coordinates, so that I know which one you're using in order for me to understand what you're doing. It's also important for you that you know what you're doing. Because if you don't introduce it, don't explicitly write it, then you actually don't know what you're doing. All right, so that's the description between the vectors and the scalars. The scalars do not depend on system of coordinates, like energy. Energy is a scalar, and it has no direction, right? That's just energy. It's there. But vectors, for example, vector velocity, acceleration, force, displacement, right? Those are vectors, and they will look different, their description will be different in different system of coordinates. The vectors themselves are not. If I have vector of velocity, this is my vector of velocity, then it is a vector of velocity, it is there. My description depends on the system of coordinates, but not the vector itself. So that's what vectors are, right? So vectors are not numbers. And so that's one of the problems of the educational system, right? Because you've been taught pretty much for like 12 years in your school how to deal with numbers, and you learn that there is like multiplication, division, subtraction, and addition, right? But they probably never told you that those operations only work with numbers, and that's it. You cannot assume that this very same operation work with everything else. But for some other objects which are not numbers, you have to invent those operations again, and they will be different, and the rules will be different, and there are objects which do not have that do not commute with each other, meaning that A times B does not equal B times A. We routinely in physics deal with such objects. It's a standard thing, right? But it's for all new objects you have to invent new math. In particular, the first objects which of different nature, not numbers, are vectors. Vectors are not numbers, right? They have direction. Numbers do not have directions. You cannot say that what is the direction of number 5? It doesn't exist, right? That question makes no sense whatsoever. Vectors, on the other hand, do have direction, right? So then you need to define how you deal with them. What does it mean to sum two vectors, right? So what does it mean to sum two vectors? Again, in order to do that, in order to understand that, you have to understand that vector is a very natural thing. It just tells you the direction and the value. So for example, one of the simplest examples of it is your displacement. I can tell you two things. I can tell you go to, I don't know, north 5 yards and then east 6 yards. So what I did, I assume that you know the system of coordinates, which is north, right, and east to the right. And I'm telling you to move 5 yards to the north. Here is a vector, right? Because it has magnitude and direction. And then I tell you to move 6 yards to the east. Your final displacement is the sum of those two vectors. That's what is called sum of two vectors. It's a final displacement. So instead of going like this, you actually can go straight here. And the result will be the same. The displacement will be the same. Right? So that's vectors. That's how the sum of two vectors is defined. You just go one, then another. That makes sense? I can do it the other way. I can say that first move 6 yards to the east and then 5 yards to north. You will, in the flat space, you will end up in the same point. And that's exactly why like summing this vector plus this vector is the same as this vector plus this vector. So they commute. I can do another thing. I can tell you move 5 yards to the north 3 times. So you take this vector and you move 5 yards, then another 5 yards, then another 5 yards. The total number of yards is 15. That's how you multiply vector by a number. And then you can sum them up again, right? So what we can do then is we can multiply vectors by numbers and we can sum up vectors. And that's it. Now we can, of course, subtract it, but subtracting, it means that I need to define what is minus vector. Minus vector is the same vector, but the opposite direction. That's all. After that, I have summation and summation and difference, right, between subtraction of vectors. And that's and multiplication vectors by numbers. And that's all. That's all you can do with vectors. There is nothing else. You can introduce another operation with them, which is called dot product. And that dot product is the following: that if I have, this is my direction, right? And I have that unit vector 1 yard to the east. Let's call it this one. It's a vector, right? It has magnitude and direction. Then if I know this vector somehow, that I know that component of the vector, it's just simply this vector, let's call it A. If I take my vector A and they take that dot product of that vector 1e, which I have 1 yard to this, that's the number which I get there, that's a dot product. It will be exactly this length by definition of it. That's how dot product is defined. Right? That's it. There is nothing else you can do. There is no such operation as taking one vector and divided by another. Right? Think about it. What does it mean to divide east by north? It makes no sense whatsoever. Because for vectors are not numbers, they have directions, so they're very special. They have their own special algebra, it's called algebra, and which defines all the operations which you can do with vectors. And the division is not there. There is no such thing. You cannot do that. Okay? That makes sense?
Mm-hmm.
All right. Now, again, this is somewhat very trivial things, right? I mean, you all know that. But when you try to work with those things, you tend to forget about it. And this is actually quite natural. I did the same thing. And only after a while you start to understand that those things are important. When you've done many mistakes on your own, you figure out that that's what it was. All right. Now there is another thing, very important thing about vectors, and the same thing about numbers also. That's how the definition starts with. Every definition of such objects which we can do, and there's some operations which we need to define, which we can do some objects, starts with the following: that we have a vector A, and we have a vector B, and we have A plus B operation, right? You know this operation. You go first along A, then along B, right? Then what we end up with is also a vector. It's trivial, right? Of course it is a vector, because that's exactly what it is. That's how it's defined. But there is a caveat here. It's not actually so. It's not always so. It's not always that you can define a summation of two vectors such that what results is another vector. It's kind of difficult to imagine, so let me give you an example. Let's imagine that you are not on a flat surface. And we are not on the flat surface, we are on Earth. It's not flat, right? You know that, right?
Yes.
I've heard that there are some doubts.
Are you sure? Are you sure?
I'm so sure that I'm most sure that on my own name. All right, so let's try to define the same thing on the on the sphere. So let's say that I do it exactly the same way as before. So here's my 1 point. Here is another point, right? And I say that this is my vector. Fine. Then I say that there is another point, and here's my second vector. Right? But now if I sum them up by the same rule, I will end up outside of Earth. Either way, I mean, either it will be on top of it or way outside, whatever you want to describe. I will not end up on the same surface. Now, if you think about Earth as being embedded in three-dimensional space, so in reality you work with three-dimensional objects, then of course they are vectors. But if I want to restrict everything just to Earth, just to the sphere, think about like if I'm an ant who lives on that sphere, and I'm two-dimensional ant. I don't have third dimension at all. The same way as we do not have the fourth space dimension in our world. You cannot point to the fourth space dimension. We only have 3. So this end, which lives here, has only 2 dimensions. It can go only along the surface, and it can go. The direction up does not exist for it. Then for this end who lives on there is no such operation as summation of vectors. He cannot introduce, or she cannot introduce those vectors at all. They don't exist. That make sense? There is a way around it, and that's what is called differential geometry, which deals with those things, and with curved spaces and so forth. And it's by the way exactly the same as in calculus. Because let's say that my end is here. Then what I do, I zoom into this area, very, very small area around where that end is. My surface is curved, but if I zoom far enough to that point, then what I will have is a flat space, right?
Yes.
That's exactly what we have. Think about your own experience. We live on Earth, which is round, which is a sphere, almost. But around us, we don't see that it's a sphere, right? We see it's like a flat piece, right? On that flat piece, we can introduce those vectors, no problem. So what you do then in differential geometry, when you try to describe curved spaces, is that you introduce on each point you introduce a neighborhood which is very small and infinitesimally small. Of course, it's a calculus idea. And in this infinitesimally small neighborhood, you can introduce vectors and deal with them. But you have to, when you move from one point to another, you also have to move this tangential space with you, and that introduces new, completely new geometry on the curved spaces. In particular, parallel lines do intersect. Sum of angles in triangle is not 180 degrees, and so forth. Right? That makes sense?
Yes, that makes sense.
So let's try to use it on a simpler example. It's the very same idea, basically. So let me do the following thing. Let me say that I have a curve. So this is my x, this is my y. It's a flat space, and I have some curve here, and I want to compute the length of this curve from point A to point B, which are given to me. And the curve is also given to me by some say I know it's given by f of x, right? Then what I do? How do I compute the curve, the length of it? I know how to compute the length of a straight line, straight intervals. This Pythagorean theorem, right? So, but it's not straight. So what do I do? What do I use?
You're saying to find the length of the curve?
Yeah.
You would do the. Isn't it the integral of the derivative of the from the bound of A to B?
But the integral of a derivative is the function itself.
Yes.
Well, the function itself, the difference between function itself will give you this fact. Right? This is the change of function. No, but what you do, I mean, stop trying to remember the answers. Think about it. What you do?
Break it up into smaller pieces.
Exactly. So let's consider a small piece here. That small piece has this distance is dx, and this distance dy, and the length of it, right? Because of that triangle. Well, let me draw the triangle. So here's my dx, and here's my dy, and this is 90 degrees. And I'm talking about the length of this piece. So the length of this piece is dx squared plus dy squared square root. Right? This is this length dl. And now I need to do it for every small interval here, infinitesimally small interval here, and sum them up. right? Because it's this length of this interval plus length of this interval and so forth. So I sum them up. That's all. That's the total length, and I need to go from point A to point B. Now, I do recognize that you probably never seen integral written this way, because it has sort of two, right? So this is two differential scale. This is the most general way of it. Let me just do some simple transformation with it. Just take the x out. So what I will have is integral, then I have square root, then I have dx. I'm taking it out. I will have 1. Then I'm taking it from here. I have dy over dx squared, right? And because now I have dx squared, I'm taking it out square root. Here is dx. Right? And so this is just a derivative of my function f. And what I have now is that length here of this equals integral square root of 1 plus f prime of x squared dx. And I need to integrate from xa to xd. xa to xd. That's all. Right? That's the length. That make sense?
Mm-hmm.
Yeah.
But you see that when it's written this way, I actually don't need to use this form of the function. Let's imagine that I have that function is given me by some other form. So let's say parametric form. I have x and y, right? And they depend on time, for example, or some other parameter t. So that my curve is given by x of t function and y of t function. Right? It's parametric form of the curve. But then I know that dx equals dx over dt times dt. And the same for dy. So this is my derivative of x with respect to t. So what I do here, I just use these functions, right? And then I say that this is dx over dt squared plus dy over dt squared square root dt. And that will be my length. Okay? That makes sense? And I can use the same thing with say, polar coordinates. So in polar coordinates, every point, so in polar coordinates are given by one line, right? And every point is defined by the length. This is not a vector, this is just the length r to the point plus this angle. So if I know r and phi, I will know what this point is. Where is this point? That makes sense? You know this, right?
Yes.
But now I can just say that what it means is that my x in Cartesian coordinates, this x, right, equals r times cosine phi. Right? It's this length. And this and y equals r times sine phi. Now I just write what is dx. Dx, because I need dx here, right, equals dr times cosine phi plus r minus sine phi d phi. Right? dy equals dr times sine phi plus r cosine phi d phi. Now I need to take the square of this and square of the other one. So let's do that. When I square them, I have square of this one plus square of this one minus twice the product of them, right? When I have square of this one, I have square of this one plus square of this one plus the twice of the product, right? The standard formula. So then what I have? What will I have? Dx squared plus dy squared equals. Now I take square of this term plus square of this term. This is cosine squared plus sine squared, right? And dr is the same. Cosine squared plus sine squared is 1. So I have dr squared. Now I go here and I take square of this one plus square of this one. Again, r and d phi are the same. So I will have again sine squared plus cosine squared. So what I have plus r squared d phi squared. Now I need to take the cross product here and the cross product here. And you can see that cross products will be the same, but with different sign because of this minus sign. So they will cancel each other. So what I have is then this expression. And if my curve is given by function r of phi, then what I have is I just pull d phi out. And what I have is dr over d phi squared plus r squared. This is also a function of phi, right? So it's r of phi squared d phi. And in order to calculate the length, I just take this integral. Okay, if I know this function, I can substitute it here, calculate derivative, plug in function, take the square root, and take the integral. Technically, it can be difficult to do, but I mean, you can always do it numerically. Does it make sense?
Yes.
So let's see what was important in these calculations, really. These all technicalities, how I go from one description to another, and so forth. But what we figure out is this. This is the main formula for us. That length equals just the integral of that square root. Right? As I actually see something in chat, if you want to ask me something, just say it. I see that there is something, but I cannot read it from here. So this is my length. So how did I? What's written here? It's a Pythagorean theorem, right? Pythagorean, right? Remember that? It was just that little piece. So let me write it in a different way. Let me write it this way. dx, dy, vector, right, has two components. 1, 0, 0, 1, is symmetric. 2 by 2, right? Okay. And here I have dx, dy. So if you now multiply it, as you should multiply vector by matrix, matrix by vector, right? You will get what's here inside. Do you see this?
Yeah.
All right. Okay. So but now see, look what's happening here. I have infinitesimally small vector here, and I have the same infinitesimally small vector over here. This matrix by itself is not infinitesimally small. It's just normal matrix. It's 1, 1. There's nothing small about it, right? And that matrix. Say again.
I was just agreeing.
All right. Thank you. So that matrix, right? It's here. It's just 1, 1. It's a very simple matrix, but it doesn't have to be simple. It can be something else. We can plug here now any matrix we want. That matrix, moreover, can be different in different places of our space. But we will still have the same thing. All right, but now just using that matrix. Not exactly the same, but using some other matrix, we can define the length of the curve on that new space which we have. For any such matrix, that matrix also can depend be different in different points of space. This matrix has its own name. It's called metric of our space. And this is particular metric. This is 1, 1, 0, 0. It's how a flat space looks like in Cartesian coordinates. In different coordinates, it will be different, but nevertheless, it will be still flat space. It is possible to actually write the same metric in non-flat space, and in particular, in my lecture notes, I actually did something like that for sphere.
Just a point of clarification. This is just the component inside the root, right? Just that expression.
And again,
That expression that you were explaining or talking about, like the whole three components. Yeah, that's just the inside of the root. That's not.
yes,
included.
right. Yes, that's the L squared, right? The L squared.
All right, I just wanted to make sure.
So yeah, thank you. This is the L squared. So you need to take the square root of it.
Yeah. Okay. Good.
Right. So then, but then can be a metric. In particular, in let me see. I don't remember those formulas. I never remember any formulas. So if you have a sphere of radius r, right, you can introduce spherical coordinates on it. So it's radius r, phi, and theta. They use standard coordinates, the standard spherical coordinates. And then this matrix will look like this. It will be r squared, 0, 0, and here will be r squared sine squared. Let me see. Yeah, sine squared theta. So you see that it's actually different at different points on the sphere. But then if you take this, plug it in here, and instead of vector dx dy, you will use vector d theta d phi. What you will have is you can calculate the length on the sphere, the length of any curve. Now, I'm not going to ask you to do that. I'm not going to demand that you become proficient in working with metric tensors. Trust me, I'm not that thing. But if you but that's actually a marvelous thing, because that metric tensor defines everything about the space, all the geometry about the space. All geometry is included in that metric tensor. And you can define, because you see that it's 2 by 2 matrix, because we are dealing with 2-dimensional spaces. But if it's 3-dimensional, that matrix is 3 by 3. It's a 4-dimensional, its matrix is 4 by 4, and so forth. You can do the geometry in any space of any dimensionality. And in particular, like those string theory people claim that our own space is actually 11-dimensional. I might talk about it later, but it's kind of counterintuitive. But they might be right. And then, well, there is no way for us to have an intuition about the geometry in curved 11-dimensional space. And the only way we can approach it is to actually with math, is dealing with that object which is metric tensor, and then build our intuition started from there. So I'm not going to ask you to do that. I'm not going to. But if you want, take a class on differential geometry. This is the best thing you will ever have. So it's but what I want you to understand is how things are defined, right? So that calculus idea of working with very, very small area, right, is very important, because every small area is flat, and we know geometry on a flat space pretty well, right? And starting from there, from that, building the geometry on a very, very small, almost flat patches, right? Bunch of patches. You can actually extend it all over any curved space and actually build the geometry on that space, right? But then you have to worry about the fact that your vectors are only defined in infinitesimally small length and so forth. So it all becomes like on top of calculus. It's called, as I said, it's called differential geometry, right? So in particular, if you know now how to compute length on any curve, we can define what is a straight line on any space, right? We can say the straight line is the line of the shortest length. If you can compute the length of any curve, then we can choose a curve which has the minimal length. Now, how to do it technically, I will describe later. There is a technique to do that. But at least in principle, it is possible. You just draw every possible line, right? Calculate its length, and do that. All right, and choose which curve has the smallest length. Now, I want to again emphasize something which is something important here. That all of this looks like a completely abstract mathematics, right? A metric tensor or something. But what it describes is exactly how you would measure a length. Think about it. If I give you a problem, I'm a professor, right? I can give you a problem. And so measure a length from here to Houston. How would you do that? Well, let's make it simpler. Well, whatever. It's not very simple anyway. So let's measure the path from here to the length of the path from here to Houston. Typical length, like how you go. You take 6 highway, right, and then to 90 to Houston. If let's pretend that's how we go there. There's some other way. So how would you measure the length of this path?
Normally, I guess you would have like maybe a mile counter, I suppose. Like if you had your wheels on your car, basically the rotation of your wheels, and you could like count how many miles, depending on how many rotations it created.
Yeah, that's correct. Of course, that will give you the answer. But I want you to be less technically proficient. Otherwise, you just ask Google. Right? If you want to go to technology. No, let's imagine that all you have is just a ruler, right? That's what we use to measure length. So then how would you do that?
You could just use like a map and then like measure each segment.
But
And then
maps,
get your distance.
you know that maps do not give you the length correctly.
Oh yeah, use the scale of the map and then convert it to the whatever length it is.
No, let's not use. You have a ruler, that's all, right? And it's those highways. What do you do? I mean, I'm not going to ask you to do that, but in principle, what should you do?
Flip the ruler over and over again on itself.
Exactly. Yes, you just go and put the ruler over and over and over, right? So what you're actually doing? You're taking a small neighborhood of every point which you eyeing, right? And you measure the length of inside this neighborhood. Then you take the ruler, move it over to the next point, and inside this neighborhood, everything is straight line. You measure the length there, right? Eventually, when you go from here to Houston, you will have some curvature of the Earth involved there, right?
Yes.
Pretty far away. But every time you actually do the measurements, you do measurements on a flat patch of that Earth. That's exactly what we are doing here. That's exactly how I describe the measuring of length. There is no magic there, right? It's what you do. It's just formulated in such a way that you can do it not just on Earth and without a ruler, but on any curved space, and actually much simpler. No sweat. You just sit in your room and calculate it instead of walking around. So all of those, yeah.
Oh, all I was gonna say is like in that case, if you wanted to know like the span that the angle from, like if you were using the radius of the Earth or something like that, would that be the only way you could get it since you measured the arc length from Houston to College Station?
It involves a little bit more. You need to find the angle between them. It's actually how ancient Greeks knew that the Earth is round. You know that in ancient Greeks they already knew that, right? It's they measured that angle in between pointing to a sun basically in two different places at the same time, right? And there's
So they had to use celestial bodies in order to figure out that there was a radius, I suppose.
Well, yeah, I mean the celestial body in that case was sun, our sun. It's good enough. Right, so they were measuring angles to the sun and the distance between the difference between angles of pointing to the sun and the distance between 2 points, two cities, and then they were able to, from the geometry, to figure out the radius of the Earth. Well, they actually made huge mistake. That's not very precise measurement. So they didn't know exactly the radius of the Earth, but they were absolutely sure that the Earth is actually round. You can do that. You don't need to go to space to see. You can do the measurements here. All right. So that's but again, what I really want to emphasize is there is no magic here. It's exactly what you're doing. It's just formulated in such a way that you can actually do it anywhere else. You don't have to be on Earth. You can use the same math anywhere else. And to describe the geometry of our universe. And the geometry of the universe is very important. We live here, right? And but before we do that, and I'm not going to do that much of that. I'm just giving you the pointers to start with your own learning if you want. But I want to ask a different question, and the following. So this is geometry, right? Geometry deals with distances and angles, right? And by the way, angles also can be defined if you have two intersecting curve. You can define the angle at the point of intersection, right? Because around that point you can take a small patch which is flat, right? And around that point, then you have two straight lines, and you can define angle between them. That's how angles are defined in the curved space. But the lines must intersect. You cannot define an angle between non-intersecting lines in curved space. In flat space, you can sort of move one line so you parallel to itself. But in curved space, that procedure is not unique. So you cannot define angles. Anyway, so the geometry deals with distances and angles. And that's the geometry of our space. It's very important, and it's connected to the phenomenon which we call gravity. But I want to ask a different question. Is there any characteristic of the space which is independent of geometry, which has nothing to do with angles and distances?
Time.
Huh?
Time.
Time?
I mean, you said a component that was independent of the geometry of space, correct?
Sorry, I didn't hear you well. So I said, what is independent?
Yeah, what is a component of space that's independent of geometry?
Right, yeah. So what's the characteristics of the space which is independent on its geometry?
Time.
Time. Well, let's forget about mechanics. Let's forget about time. We're talking about spaces only. Time is a difficult concept, and it can be included in the geometry, and that's what Einstein did. But I don't want to. Let's simplify it. It becomes a little bit more too complicated for one lecture. So let's consider just the geometry, just different spaces, curved spaces, right? Let's stick with two-dimensional space. Like one of them is sphere, right? So is there any characteristics of that two-dimensional space, two-dimensional surfaces, if you will, right? Which is independent on the geometry? Can you think of anything like that?
I mean, the first thing that comes to my mind are like the scalar quantities of like the links, but
Yeah, exactly, right. But I just specifically said that length should not be involved.
no,
We
yeah,
don't want to define geometry yet. In a sense, it's more basic in geometry. Well, there are a few things. A number of disconnected pieces. I have one sphere, and I have the other sphere, and I call both of those spheres my space. So it has two disconnected pieces. The number of pieces is, of course, does not depend on whatever lengths I use, right? It's just the number of pieces. But it's sort of trivial and it's not interesting, right? It's different pieces, whatever. So let's imagine that we have only one piece. And so is there anything you can think of? Okay, let me give you an example. One of them is a sphere. And the other one is a torus. Is there any difference between them? Which is do not depend on scales or anything. Come on, guys, you can see them, right? Is there any characteristics which makes them different?
One has a hole.
Exactly. Come on, the most trivial answer is the right one. One has a hole in it, and this one does not. And that's completely independent of how I measure distances in it. Or how I define distances in it. Right? So in this sense, this is more fundamental property. It's a more basic property than geometry itself. It's the global structure of that space. Does it have holes or does it not have holes? Okay? Now, the question which I want to ask is the following. Let's imagine that again, I'm that end who lives on that space, and the end knows nothing about the third direction. That the direction perpendicular to that space, perpendicular to the surface, does not exist for that end. It cannot look up. It cannot look down. It cannot see up. It can only see along this surface, and only can move along this surface. Right? The same as for us, fourth space dimension does not exist. We cannot move along fourth space dimension. So that's the same for n, but just simpler because it's only on 2 dimensions. So how could that n tell between this and this structure of his own space? That n lives there, right? It wants to know if your space has holes in it. How would he do that? How would he know that?
Would go to the center, I guess.
What is the center? Center of what? What is the center on the sphere? You have on the surface, right? There is no third dimension. You can live only on the surface. So where you go? Where is the center?
I mean the middle, the
You can't go into the middle because of the fact that, like, since you're looking at those close approximations, it would always be like just two-dimensional. So
Yeah, you don't have any middle. I mean, think about it. That description does not depend, whether it has hole or not, does not depend on geometry, right? So in particular, that sphere is not necessarily a sphere. This doesn't have any holes either. I mean, I can think about it that it's made of Play-Doh, right? And I can change its shape any way I want, as long as I don't cut it and don't glue them together, right? Because if I glue them together, I can actually change from here to here. And that I don't want to do. If I cut it here, right, then I change from have a hole to not have a hole. Right? So I don't want to do that because I want to distinguish between them. So, but then otherwise I can do whatever I want. I can have the Play-Doh, and the only thing which I cannot do is cut and glue. So how do I know that if my piece of glue and I'm living on surface of it, and the surface is the only thing which I can measure, or I can do with, I can deal with. How can I know that whether my world has holes or not?
run along the borders.
What is a border?
Professor, this may be dumb, but I guess the one that has a hole in it, at the point where it caves in, it's going to be flat on the top and it's going to make a circle. Whereas the object that doesn't have a hole, you're not going to have any of that flat portion, if that makes any sense.
Okay.
That may be kind of thinking a little too much.
I said that it's made of Play-Doh, this one, but this one also is made of Play-Doh. So there's no circles there.
Yeah,
I can change its shape.
Okay, yeah, never mind. I was kind of.
Now, it's it's not surprised that you cannot answer this question, because this question is really hard. It does have an answer, and I'm going to provide it, but it's completely not trivial.
Wait, could I try one more thing? Is it
Okay.
if they do the measurements with the ruler, they could compare the distances that they travel in their two-dimensional space to see if they're the same?
But again, it's made of Play-Doh. It doesn't have a shape.
Oh, that's right. Yeah.
Right?
So
So what
it's malleable. Yeah,
Yeah,
I see what you're saying. Oh,
But you see that it doesn't matter what shape it is. It either has a hole or does not have a hole, right? It's that distinction still stands. But any measurement of distances will not give you any answer here. It's before the geometry is defined, right? So there is no idea of distance here at all. So let me start answering this question, and I hope I will make it through. And it's actually called Euler characteristics of a surface. That's exactly what we will try to describe it. But what I want to do, and in order to do that, I have to start from completely different story, which has nothing to do with all this thing at the first glance. All right? So what I want you to do now is the following. Take a cube. Just a normal cube, right? The cube has edges, right? It has edges, it has faces, the sides, right? And it has vertices, that point, where edges meet. Here. Does that make sense? Do you understand that? So there is vertices, there is edges, and there is faces. There are faces, right? Right?
Yes. Yes.
Okay, good. Now, what I want you to do now is to calculate how many vertices a cube has. Come on, give me an answer.
8.
8.
Good. Thank you. Now, how many edges does it have?
12.
10.
Okay, let's count. We have two answers, right? So it's 4 here.
Yeah. 10. Wait.
4 here, and 4 here. 3 times 4 is 12. Right? We count all edges. We have 4 on top, 4 on the bottom, right? And 4 on the side. All right. How many faces do we have?
6.
How many?
6.
6, right. That's, I think, is correct. Yeah, 6. Now, I want you to compute the following thing. Take the number of vertices, subtract the number of edges, and add the number of faces.
2.
What do you get? Huh?
2.
Good. All right, this is 2. Okay, this is called height. It's called Euler characteristics. Now, I want you to do exactly the same exercise. But for tetrahedron. Tetrahedron, right? It's called this one. Like it's a pyramid with a triangle on the bottom. So let's do that. What is the number of vertices?
4.
4. What is the number of edges?
6.
What is the number of faces?
4.
4. What is that combination for it?
2.
Again, 2. All right? Don't you think it's a bit odd? It is the same number.
So does that apply to all shapes in the world?
Almost. No, not really.
Oh,
But yes. Let's say that what you would call shape, it will. So it's called Euler characteristics, and I will say why it is characteristics. But if you take any other object like that, like I don't know, octahedron, whatever else, whatever hedrons you want to do, and you count those numbers, you will get exactly the same number 2 for that combination. Okay.
Now, I've forgotten it. Would a sphere be considered a type of polyhedral since it?
Not yet. No. Polyhedral has vertices, edges, and faces, right? Sphere doesn't have anything like that.
Even though like as you would approach like
Yeah,
like
that's the next step, right? That the limit in the limit it will. But for now we just using the simple kids exercises, right? I actually never could understand why they teach those kind of things in the elementary school. You just count the number of edges, right? And that's easy. So the funny thing is that no matter what you get, what figure you draw with edges, vertices, and faces, and you compute number of vertices, number of edges, number of faces, you'll get and this combination, you'll get exactly the same number too. I'm not restricting you to any special figures. It doesn't have to be any. It doesn't have to have any name. It doesn't have to have any symmetry. It really doesn't matter if you throw any edges, any faces, and vertices there. You construct like some surface out of them, and you compute this number. You get 2. That absolutely doesn't matter what you do. Let me prove it to you that it will be so. Let's imagine that we have some figure of that polyhedron, I think it's called. So there is some polyhedron. It can have million edges, million vertices, faces, whatever, right? So let me consider there is one face in it. Whatever it is, I don't care. Right? Let me then take that face, one face out of that huge polyhedral. And let's imagine that polyhedral has this, we computed its number for all of that, right? And it's some number cut. What I want to do now, I want to draw an edge, one more edge here. And I want to see how that chi will change. Okay? That make sense? That make sense?
yes.
Yeah.
So I had initially here, right? I have some edges and some and a face, right? And some vertices. And I don't care how many of them. So now I take it and I draw one more edge here. What happens? You see that I increased the number of vertices by 2. Right?
Yes.
So the delta V, the change of the number of vertices, equals 2. Now, the change, I used to have one face. Now I have 2 faces. Right?
Yeah, which means the delta F is 2.
It's 1. It was 1, now it's 2. So the change of the number of faces is 1.
Oh, yeah.
Right? Now I want to compute the change of the number of edges. Right? So before I had this edge and this edge here, and the rest of them which I don't touch, so they don't change. But so it was 2 of them, right? But now I have this edge, this edge, this edge, and this edge, and this edge.
So 3.
Yeah, so it's now 5, right? Instead of 2. So delta E equals 3. Right?
Yes.
So what is delta chi then? Delta chi, it's the previous chi, it's new chi minus the previous one. It will be equal to change in the number of vertices minus change of the number of edges plus change of the number of faces. Can you calculate what it is?
0.
It is 0, right? So chi does not change when I draw one more edge. So if it doesn't change when I draw edge, it means it doesn't change when I delete it. Right?
So as
Yeah, makes sense.
you would continuously approximate it as the limit approaches infinity, the relationship should still stay.
Yes, exactly.
2.
Yeah. But let me before we go there, let me say that this is not the only possibility. Right? I can, if I have some face, I can draw a new edge from this edge to another vertex. Right? And there is another possibility that I have a face and I draw a new edge from one vertex to another vertex, which already exists. For all those 3 cases, I need to compute the change of delta chi. And my statement is only correct if for all of them, delta chi equals 0. Right? Otherwise, I can add an edge and then change my chi. So I leave it for an exercise. And I think it's a fun exercise to do. So just consider those other 2 cases, and you will see that delta chi actually does equal to 0 in all of those 3 cases. So it really does not matter if I add my one edge anywhere or subtract one edge, delete, like erase one edge anywhere. It will still, chi will still be true. And then exactly what was said, I don't know who. I mean, I don't know. It's just my speakers. So I can now take the cube, right, and throw many edges on it. And in this way, I can approximate in the limit of infinitely many edges. I can approximate this sphere, right? And then I can say that, well, because like on every step on that procedure, I increase number of edges more and more and more. On every step of that procedure, chi will always be 2. Then in a limit on infinitely many edges and vertices and faces, of course, I will still have chi equals 2. So that limiting procedure allows me to say that chi equals 2 here. And if I want to do the otherwise, like I have a sphere, I want to compute chi, right? All I need to do is to take it as a Play-Doh, right? Make, I don't know, cube out of it. Change its shape any way I want, as long as it has edges and vertices and faces, and I can distinguish between them, right? So I make that sharp object out of it by thinking about it as a Play-Doh, right? And just simply compute number of faces, number of edges, number of vertices, and compute that Euler characteristic. And that will be the Euler characteristic of my sphere. Does that make sense?
Yes, sir. Yeah.
So it's but notice that in order to compute that Euler characteristic, I know nothing about distances whatsoever. All I do is just counting vertices, edges, and faces. There is no idea of distance here.
Professor.
Right?
Professor, but a sphere does not have any vertices, right?
That's what I'm saying. All you need to do is to take that sphere, think about it as if it is made of Play-Doh, and change its shape into, say, cube. You can do that, right, with the Play-Doh.
Okay.
Then you have edges, vertices, and faces. And
Okay.
you just simply count it. That makes sense?
Yes, thanks.
So the whole idea is that by the way, that change of shape in this way without cutting or gluing is called diffeomorphisms in topology in math. I'm not using the strict definitions here, but that plane door intuition is good enough for our purpose. So it tells you that there is some characteristics which we can assign to any object, and that characteristic will not depend on the shape of the object. Because if it's not a sphere, if it's something else, like a beam, right? Shape of a beam, I still can do the same thing. Assume that the Play-Doh, make a cube out of it and compute it and calculate everything on the cube, and it still will be true. The other characteristic. So no matter what I have, I can do that. Right? But then it's sort of questionable, so what? If it's always 2, why bother? In order to do that, in order to see why bother, I want to do a different thing. I want now to take the torus, the donut shape. Right? You see the donut here, right?
Yes.
So I want to do the same thing. I want to assume that there is a donut. It's made of a Play-Doh. You've made a donut out of Play-Doh probably in your life, right? And now I want to start, and I want to take it and change its shape into something which has vertices and edges
Coffee
and
mug.
faces. Say again?
Like if I know a donut can go into a coffee mug from that class I took, but that's that's if it
All right, so you have that shape, right? And you just take it and make say this figure. And I don't know, can you see it?
yes.
It's like that square cross section, right? And it goes like this. Right? I mean,
Yeah.
anyone who cannot see that thing. I actually have the same picture on my lecture notes, and I try to do it better there. Right, so I took my donut, right, of a Play-Doh, and I changed its shape this way. Now it has vertices, it has edges, it has faces, and I want to calculate it, compute it, right? If I do that in this picture, that will be a mistake. And the mistake here is subtle. So it's let me explain it. You see that if I do that right here, I have to assume that this is my face, right? One of the faces. But that face has a hole in it. It looks like that, right? If I just take the face, it has a hole in it. Right? That will be my face. And this is a bad thing. A face must not have holes. I must introduce edges in such a way that it does not have holes. The face does not have holes. Is it clear?
Yes.
So it's actually easy to do, right? You just introduce edges like this. Right? This is my one face, and it has no holes. This is another face, and it has no holes. And this is another face, and it has no holes. So now we can do that. So after all, I have no faces with holes. You know, after I've done it, I can now count the number of vertices, edges, and faces. Let's do that for this figure. Again, let me repeat. I took a donut, right? I made that figure out of it, that shape out of it. I made sure that I draw the edges such a way that there is no holes in any face. And now I can All my faces are holeless. And now I can calculate exactly the same thing. So what is the number of vertices here? So it's easy to calculate, right? Say again?
6.
It's actually 12. So 1, 2, 3, 4, 5, 6, right? It's 6 on top, but there is also the bottom line, the bottom surface, right? So it's 12. Don't forget about the bottom. The bottom is exactly the same as the top. So let's compute the number of edges. So what we have here, on the top surface, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 on the top surface, the same number 9 on the bottom surface, right? And now we need to compute those side edges. 1, 2, 3, that one, and then 1, 2, 3. 6, which is 24. Now we need to count the number of faces. I have 3 faces on top, right? Of faces. 3 faces on top plus 3 faces on the bottom. Then I have 3 faces on that side. From outside, right, on side faces. And I have 3 faces on the inside part. So it's total 12. Right? That makes sense?
Yes.
Yeah.
Now what is the chi for it?
0.
You see, it is 0. So the chi for the torus is 0. Right? And again, remember that when I added edge, right, I added in the previous proof, I added locally, like on one face. So I can add any edges here again. And exactly the same thing will work out. Because the agent of H knows nothing about how many holes in there. It just doesn't change chi. That's all. So again, I can introduce many edges here, make it as smooth as I want, and approximate my my torus any way I want. And at every step, I will have chi equals 0, so that for the torus chi equals 0.
Did you just say that chi wasn't dependent of the amount of holes?
Say it again.
Were you saying that the amount of holes determines the like what chi's value is, or just that the presence of a hole?
Exactly. Knowing that chi, we actually know the number of holes. Again, let me prove it to you. Let's imagine what is the hole. Well, first of all. So let's imagine that we have that polyhedral, whatever it is. Right? And let me draw it a different way. But now it has, and it can have many holes or whatever. I don't really care about at this point. What I care is that there is one hole which I want to consider. It is not a hole, but it will be a hole if I connect it like this. Right, with some and let me make the connection as some sort of triangle prism. You see? So now it has a hole, right? And remember, it's not necessarily a triangle prism, but because it's made of plate dough, I can always make a triangle. So I can take that for example, that part here and make a triangle piece out of it, triangle prism. Right? So it shouldn't matter. But now, let me get rid of one of the holes. How do I do that? Well, I just cut it, right? Something which was not allowed before. But this is the only way to get rid of a hole. I need to cut. my Play-Doh. Right? So let me do that and see what that cutting, which was not allowed before, but now I want to see what it actually does to cut. So let me cut it here. And then what I will have, I have a triangular prism coming here, right? And it has it now has this kind of shape. So let me write it like this, so, right? And there is another triangular prism which is coming here, and it also has this. And you see that if I glue them together, I get this one. Or if I cut this one, I get this one, right? So again, let me assume that there is a chi here, some chi. And that chi includes in that, there is no vertices here, originally vertices just on this piece, right? There is no vertices, there is 3 edges and 3 faces. And no vertices, right? Right? Just on this piece. Do you see this?
Yes.
Now let's compute what we have here. We have here 6 vertices. So on that part, I have v equals 6. So my delta v, right? The change of number of vertices is 6. So I have delta v equals 6. Now, how many edges do we have? 1, 2, 3, 4, 5, 6. Right? 6 edges here, 6 edges here, 12. But I had 3. So my delta E, the change of the number of edges, is 12 minus 3. 9. Right? To make it numeric. What did I call the edges, right? 1, 2, 3, 1, 2, 3, 6, 12 minus 3, 9. Okay. Let me calculate changes the number of faces. Now, I had 3 faces to begin with. Now, how many I have? I have 1, 2, 3 on the other side, and 4. Right? On that side. I don't know how it's called. This one. Right?
Yeah.
So it's 4 here, 4 here. So it's total 8. Minus 3, which I started with. So it's 5. Okay? So after the cut, then, what is the delta chi? How is the delta chi changing? Well, it's 6 plus 5 minus 9. What is it? 6 plus 5
Me
9
too.
minus 9, it's 2. Right? So every time I cut, I made a cut. I increase my chi by 2. Right? So chi was 0 here for the torus. I cut it. I got something which is exactly the same as a sphere, right? And my chi must increase by 2. That's exactly 2. Right? Does that make sense?
Yes.
So you see that cutting increases by 2, right? Then gluing decreases by 2. Decreases chi by 2. But every time I glue something like that, right, I produce one more hole. So it's actually a number of holes. The number of times I glue it. So what I then have is that I have some object with G holes in it. Then my chi will be equal to 2 minus 2G. That G is called genus of the surface. And that's what Euler invariant is. Right? So remember then, how can I compute a chi, right? I take my shape, I make a polyhedral out of it, just assuming that it's made of Play-Doh, right? Make sure that there is no holes in faces. That's important, very important. Right? And then I actually, and then I just compute number of vertices, number of edges, number of faces. And I got some number. And that number actually immediately tells me how many holes my surface has, or how many handles. Actually, people usually talk not about holes, but handles in this surface, right? So now, returning back to my end, that little end who's living here, what does it need to do? All it needs to do is to draw a net on its surface where it lives, right? That net is polyhedral. So it can do it completely arbitrary. It really doesn't matter how it does it. Just draw a net, anyone, any net, right? And on that net, that smart end counts number of vertices, number of faces, number of edges, and computes chi. And knowing that chi, he will know how many holes his universe has. That make sense? Does it make sense?
Yes.
Right, so I think it's very, very cute piece of mathematics, very, very simple one, right? And all the proofs which I gave here are also very simple. They can be done by I don't know, and now let me say something else. First of all, this is the way how, in principle, right? We should know if we have wormholes in our universe. Our universe has some shape, and a wormhole is exactly that hole is exactly handled, right? So we can draw a map, draw it in that net. Unfortunately, we have to draw a net in a space-time, right? Because the space is not enough; it must include time, and it's very difficult to draw a net in a space-time. I don't know how to do that. No one knows. But in principle, it's possible, right? And if we could do that, we could know if we have any wormholes in our universe. If our universe has some sort of strange holes in it. That's one thing. Another thing, our universe will be, if we include time especially, would be 4-dimensional, right? And as it is, only space is 3-dimensional. This is only for 2-dimensional cases, which I consider. But if you now look at this, this is a vertex. It's a point, right? It's a 0-dimensional. This is 1-dimensional object, edge, right? It has only one line, and this is 2-dimensional object. So you can easily continue it later on. You see that the sign are just changing: plus, minus, plus. The next will be minus, and so forth. So you can actually define the same characteristic for any number of dimensions. But there will be, instead of faces, there will be what is called simplexes. So, and last point I have, I think, 1 more minute, I want to make is I want to, you can probably think about what does it have to do with physics. And, but I try to say that, well, universe, blah, blah, blah. But in reality, it's actually a lot more important for physics. Think about it. What I just told you, that there is some characteristics here which is completely independent on the details of my space or whatever that space is. Right? Such characteristics are called topological characteristics. It's what I try to describe here is one of the topological characteristics. But it does not depend on details. Right? So it is insensitive to details, in other words. Think about it. If you want to construct a memory, a very good like computer memory, that if you find a way to use that topology as a memory element, like has a hole in whatever space, it's not real space, it's some other space of wave functions or something like that, quantum mechanical. But if you find something which has that. There is no hole as a memory element, 0, 1, right? Then this memory will not depend on the details of your device. It will not depend on temperature. It will not depend on any local perturbations which you have. It will not depend on very much on the manufacturing processes. It will be very, very robust because like local perturbations like temperature will not change anything.
You're talking about like the performance of the memory?
I'm talking about like a new way to build the memory device. And that's exactly what people are trying to do. Right now, there are like bunch of people, including myself, working exactly on that kind of problems. Is to find some way to write the memory not on some topological properties of some fields, like let me call it. So in that way, that memory will be very robust. It could be made very small. The biggest problems with current ideas of memory, which you choose all your computers, is that you cannot shrink them down. Eventually, if you shrink them down, the noises, either thermal noises or quantum or even quantum mechanical noises, become too big. And so your memory, if you have a noise, your memory can flip from 0 to 1 spontaneously. And then memory it's not a memory anymore, right? And you don't want computers to forget. So the idea then is to find something which cannot be flipped by any noise. And the topological structures of some fields, it's one of ways of doing it, because it's completely insensitive and it cannot be destroyed by any local perturbation, any local noise. And then if we find out how to do it, and then find out way to do that, then we can shrink that memories a lot further down to quantum mechanical level. All right, so in contemporary physics, that kind of topological considerations are becoming more and more important. And basically, I don't know, about half of the physicists of the world right now are working on some stuff which is related to topology one way or another. All right. Sorry, a little bit over time. Any questions?
So, Professor, what is the hole supposed to represent?
Well, in the surfaces, it is it's just a hole, right?
Right.
But I mean, if I try to describe you what exactly in quantum mechanics or that kind of physics which I try to tell about for memories, what the topology is there, it will take more than one lecture.
Okay. Thank you.
It's not very complicated, right? There is nothing complicated. I tried to tell you there is nothing really complicated there. It's just all like like skill. You need to learn it. You need to work on it. It's not very complicated, but it will take a lot of steps to actually come there.
Okay.
Okay, so I'm sorry, I do not have time.
Thank you.
I wish I could. I mean, it's a fascinating story.
Professor?
Yeah.
I said a question. So earlier you said whenever you make a cut, it's going to increase chi by 2.
Mm-hmm.
But when you glue it back together, it decreases by 2?
Yes, of course. That's a reverse process, right?
Uh-huh.
You cut it. So if you first glue it, then cut it, you come back to where you were.
Yes, yeah.
So if one of them decreases, the other one has to be increased, right?
Okay. But like in the case of like the circle, when you start at like chi 2, and then you cut and make it into like a donut, and it's chi 0, isn't that decreasing it by 2, or is those
No.
like?
Just a second. First of all, I don't have circles. Circle is one-dimensional.
Oh, sorry, sphere.
I cannot cut a sphere to get here. Right? I can make a cut here. Then what I will have, right, is something of that shape.
Yes.
And then if it's Play-Doh, right, I can take this shape and convert it back to sphere.
Oh, okay. Okay, that makes more sense. Yeah,
So
I was looking at it wrong.
I cannot drill a hole, right?
Yeah.
I don't drill. I cut.
Okay, that makes more sense.
Okay. Yeah.
Thank you.
Thank you, by the way. It's a good story. I don't drill. That's important.
Okay, I was wondering about that.
Yeah, good. Anything else? All right, that's it for today then. I have a office hours today at 1, right? So come if you want.
Just a quick question about office hours. Is it only strictly virtual, or did you say physical were fine?
You see, it depends where I am, right? And so if you want to come, send me an email and I'll wait here. Although I'm getting very hungry, to be honest.
Okay.
I was planning going home. But if you want to meet with me, well, yes, please. And by the way, if you want to meet with me, just tell me that. And for example, right after lectures, I'm here, and you can come by. Really, office hours is just some time which is we sort of agree. But if you want some other time, just tell me, and I'll do it. Right? But if you want to meet with me, like personally, it's probably easier to either before lecture or right after.
Oh, okay. Are you available right after lecture for a couple minutes?
Yeah, sure.
Okay. Thank you.
I'm here. All right. Anything else?